not like it's a big deal. Anyway, all right, today we are beginning our fourth lecture. We're going to finish our discussion of the method of joints, which is on our Moodle page right here. Okay, so we have a handout for the method of joints right here. So this is what we're referring to. We're just going to briefly finish up, and then we're going to move on to the handout for the method of sections. Today is our fourth class period, and so after today we'll have our fifth class period, and then this homework will be due before the sixth class period. So we'll spend today and the next lecture 5 talking about the method of sections, which builds directly on the method of joints. Then I will have a homework assignment posted that will be from the two handouts, from the method of joints and the methods of sections. Then we'll begin chapter 1 from our textbook. So now that we know where we're going, let's go there. So we talked about the method of joints last time, and we started to do one problem. So I had done problem number 6.10, and I'd asked you guys to do 6.11. And there was a lot of progress made. So the last thing I'm going to do on method of sections, method of joints rather, is to complete this problem in class so that you have it in the lecture notes as well. And this is going to build directly on what you had done in class. If you're in cyberspace, you did not participate in that. So in about 15 minutes, you will have this material in your notes as well. So I'm going to move over to the document camera, and we're going to start working through this problem. Okay. So for problem, and this is the method, every single time you want to do a free body diagram of the entire structure. And when you do that, you can solve for external reactions. So after you have those external reactions, you will do a free body diagram of individual joints or on individual joints. And when you do that, you will solve for internal reactions. Okay. And then you will decide whether those internal joints are in compression, meaning that they are pushing on the joint. So it's all from the point of view of the joint, or tension, which is pulling on the joint. And then at that point, all you have to do is just write your answer. Number, unit, tension, or compression. And so that's the process that we will follow. So let's look here at 611, which is the problem that you solved since you were working on it in class. I'm going to go fairly quickly. I would ask you the numbers. Do you guys have any of the numbers, or did they all get erased and are therefore erased from memory? Okay, we're tabula rasa. We are a blank slate today. Gotcha. So we have a triangle that's 3 feet, 4 feet. We have a fixed support at A. Since it's a fixed support at A, we could have a reaction at A in the X direction and a reaction at A in the Y direction. We have a rolling support at B. So we only have a reaction at B in the Y direction. We then have a 300-pound force acting in the negative Y direction and a 500-pound force acting in the positive X direction. So we begin, because this has static equilibrium, summation forces X must equal 0, summation forces Y must equal 0, and also the summation of moments about any given point will also equal 0. And I just use the sub-0, just meaning any point. So in the X direction, remember, country western song, that's my story and I'm sticking to it. This is how I have my reactive forces drawn. I draw the picture. Even if I'm halfway through and I think, ooh, I think that is the wrong direction for a reaction, I stay with the direction that I've drawn in the picture. The math will play out, and in the end, I'll know if I've chosen correctly or not. If you decide to change horses in midstream, then you need to redraw your picture. So let's just go with keeping it the way it is. In the x direction, I have RAX, which I've drawn as positive, and I have 500 pounds here, and these other forces externally are y. So I then find that RAX is equal to negative 500 pounds. Means RAX looks like this, 500 pounds. Now let's do my y's. Negative 300 pounds applied here, positive RAY, positive RBY equals 0. So I know that RAY plus RBY is equal to 300 pounds, but I can't determine which is which. One equation, two unknowns, no bueno. So I need a third equation. So I'm going to choose to take moments about A. Summation moments about A equals 0. The reason for that is it eliminates the most number of moments caused by forces. The 300 pound is collinear. RAY and RAX have no moment arm, so all of those produce moments that have a value of 0. So all I have is RBY, which is vertical, operating through a horizontal moment arm of 3 feet. When I put a pin here and I think about RBY, the way I have it drawn, it will be counterclockwise, which is positive. Then have the 500 pound force, which if I look at that, put the pin here, pull on the 500 pound force, that's going to be negative because it's clockwise, negative 500 pounds times its moment arm. Since this is horizontal, the vertical moment arm is 4 feet. Those are the only two forces creating moments about A. They have to sum to 0. I want to solve for RBY. Times 3 equals 500 times 4. Therefore, RBY equals 500 times 4 divided by 3. 4 and 3 are both feet, so those cancel out. I'm left with units of pounds, which is a good unit for a force. 500 times 4 is 2,000. Divided by 3 is 666 2/3. So that value of RBY is 666.7 pounds, or we could say approximately 600, just for the sake of argument, 667 pounds, if I round it to single pounds. It also tells me that I have chosen the direction correctly. Okay, so now I know RBY. I can go back to my summation forces in the y direction, and I can then compute my RAY. So RAY plus 667 equals 300. RAY then equals 300 minus 667, which is negative 367 pounds. That means that I've chosen that incorrectly. RAY looks like this. Its value is 367 pounds. RBY is 667 pounds. And I've therefore solved the truss. Okay. So now I'm going to draw a clean free body diagram. And I'd just like to reiterate that your free body diagram is part of your solution. So good, clean, simple diagrams. I always refer to this as an engineer's version of a stick figure. You know, like if you think about a person, you know, they have features, they have clothing, they have hair of a certain color, they're, you know, dressed a certain way, and this is how an engineer sees them. This is a stick figure that represents a human being. And I always refer to this guy as Ernie. So this is Ernie the Spokesmodel. So Ernie the Spokesmodel is this equivalent. We have a truss with some features, connectors, etc. Ernie just looks like this. My free body diagram just looks like this. So I have RAY equal to 367 pounds acting downward. RAX has a magnitude of 500 pounds acting to the left. RBY has a magnitude of 667 pounds acting upward. Then we have an applied load of 300 pounds acting downward, 500 pounds acting to the right. And if I've done the math correctly, everything should balance out. This is incorrect. This would be, the way I have it drawn, my 300 is acting upward, so I have to see what I've done incorrectly here. These two add, so do you see what I'm saying? These two, the y direction does not sum to 0. So Ernie is telling me I have a mistake. So let me figure it out here. 667, no, it's correct. This is pushing up, these two are both pushing down. These two add to 667, so it is correct. Okay, so Ernie's still happy. All right, now what we need to do is to determine what is the internal response, the internal load in AC, in AB, and in BC. So to do that, I break it down into looking at a joint. I'll first look at A. So what do I have? I have a 500-pound force acting on A this way. I have a 367-pound force acting this way. I have some reaction in AB, and I have some reaction in AC. All right, well, this is kind of interesting because it's all horizontal. I have two horizontal forces and two vertical forces, so they have to oppose each other. If this is 500 pounds this way, AB is the only one with a horizontal component, so it has to be 500 pounds this way, and it is pulling on the joint, meaning that it is in tension. AC, if I have 367 operating downward, this has to be 367 operating upward. Also, because it's pulling on the joint, it's in tension. So the only one I have to determine now is BC. I can move to joint C or I can move to joint B. B is slightly easier because here we have two applied forces and two internal forces. Here at B, we just have a single force. It's not significantly easier, but it's slightly easier. So at joint B, we have BC, which is my unknown at this point. I have AB, which is known, and I have a load pushing up, which is also known. So this is 667 pounds. Now let's look at AB. I know that my magnitude is AB. I know that it is pulling on the joint. At joint A, that means that it looks like this, but at joint B, it looks like this. In other words, it's still pulling on the joint. So now let's determine the direction of BC. This is my only force that has an upward component or a y component. It's upward, so this has to be downward. Has to be. That also corresponds in the x direction because this is to the left, this is to the right. So it's all going to work out. So to find BC, summation forces x have to equal 0. Summation forces y also have to equal 0. BC has an x component, so I don't know what that is yet. I'll have to do a little trig. But BC and the x then minus this force, which is 500 pounds, equals 0. I could also use my y directional force where I say negative BC in the y direction because it's downward plus 67 pounds equals 0. It is irrelevant which of these I use. I have to solve for BC, not BCX, BCY, but just BC. So I'll use this. It is irrelevant which one you use, but I'll use this. And I'll say then that BC in the x direction has to equal 500 pounds. What is BC in the x direction? Here's where the trig comes in. This is BC, this is BCX, this is BCY. This is, remember the shape of the triangle? Oops, there we go. since BC force is directed along BC member, this is also the shape of this force triangle is the same as the shape of the physical triangle. So BC in the x direction, this component, if I want to take the whole BC, okay, that's the hypotenuse of a triangle. This is the adjacent to this angle. Adjacent hypotenuse equal cosine. So BC in the x direction is equal to the entire force in BC times the cosine of this angle, theta, whatever that angle is. Cosine is, there's a couple different ways I can just find that angle explicitly, right? So I can say theta is equal to the inverse cosine of 3. You know what? I don't even have this. I do know, I'll tell you something else in a moment. But since this is opposite and adjacent, I can say the inverse tangent of the opposite side, which is 4/3. And I can say then that theta is equal to whatever this solves to. That's the most explicit way to do it. And so if I take a look and I say, I just want to find the inverse tangent, tangent minus 1 of 4/3. That is, oh, that's in radians, sorry. What is it? Do you know what that angle is? I guess I can just use my radians. 2.07. I just want to get my calculator back here. Hang on just a second. All right, so let's see if I've got a tangent function. There we go. I want the inverse tangent. It's going to be harder than I thought. This is my inverse tangent, and my factor, my argument is 4/3 equals. Okay. And then I want the inverse tangent of that. Tangent. Oh, I know. Clear it out. So I want the inverse tangent of 1.333 equals. Oh, come on, stop it, you're bugging me. Inverse tangent. There we go, 53 degrees. So that tells me that my angle is 53 degrees. I'll show you a slight little shortcut here in just a moment. But so that means that this angle is 53.123 degrees, but roughly 53 degrees. Okay, so that means that BC of x is equal to BC times the cosine of 53 degrees. Once again, this is the most explicit method to do it. Right here. Or BC is equal to BCX divided by the cosine of 53 degrees. Okay, so the cosine of 53 degrees, according to my calculator, is 0.6. So if I take the value of, I want to take BCX and divide it by that, I know that BCX is 500. So, oops, you can't see what I'm talking about right here. Okay, so BCX is 500. If I take 500 and I divide it by the cosine of 53 degrees, which is 0.6, I'll get the value of BC. Okay, so come back over here. So I take 500, I want to clear this. Clear the entry. There we go. So I go 500 divided by 0.6, and that value is 833. So that means that BC has a value of 833 pounds. Okay. So here this is 833 pounds. If I go back, is it pushing or pulling on the joint? It's pushing. So that's compression. Okay, so to solve the truss, I can say AC equals something, AB equals something, and BC equals something. So AC, we determined, is 367 pounds in tension. AB is 500 pounds, also in tension, and BC is 833 pounds in compression, and this block of information is the answer to solving that truss using the method of joints. Okay, now I went through a little rigmarole here that was a very explicit trig solution in case your trig is a little bit rusty. But here's another thing that you can do, just to shorten it up. It's exactly the same thing. But if you have a right triangle which has legs of 3, 4, and 5, does anyone know what the length of the other side is? I already said it. It's 5. Anytime you have a right triangle where one of the legs has a length of 3 units, the other has a length of 4 units, the hypotenuse is going to have a length of 5 units. So that type of a triangle has a 53-degree angle here, and then 90 minus 53, which is 37 degrees here. But instead of going through this rigmarole and computing sines and tangents and the actual angle, what can you say here? Well, if you're conversant with your trig, you can say BCX is equal to BC times the cosine of theta, but cosine is adjacent over hypotenuse, so that's 3 over 5. So you could then say that BC is equal to BCX times the reciprocal of this, 5 over 3, right? And so since we know that BC is, or BCX rather, is 500 pounds, 500 times 5 divided by 3, and if you do that math, you'll see that BC is equal to 833 pounds. Okay, so you can do this if you're comfortable with trig without actually using your scientific calculator at all, which would be my inclination, but that may or may not be familiar enough to you. So you do either way, whichever math is more sensible to you. All right, do you have any questions about this? So there will be homework problems, right? That's the next part. Let's go back to our handout. Method of joints. We've done 610 and 611. We really only need to do a couple of these, and then we will do method of sections. So it will become quickly apparent to you why you wish to do the method of sections in certain cases. For your homework for the method of joints, and this will be, like I said, it will be due next Tuesday, which is September 4th, by 11:55 p.m. Mountain Standard Time, or whatever mountain time we're on right now. I think they're still standard. Are we standard or daylight? Are we on daylight time still? Maybe. I don't know. Whatever. I'm just going to put mountain time. We'll just, whatever it is. Right now it's 10:30 in the morning. So anyway, and please submit through Moodle. So there will be a Moodle button for you to do that. Okay? We're just going to have a couple of problems, then we'll have a couple of problems with the method of sections. But for the method of joints, I would like you to do from your handout 614. And then a larger truss. There's something here that you'll learn when I'll talk about in just a minute, and 621. Okay, so just those two problems. Now you can work on these together if you would like, but each of you will have to hand in a separate homework. Now there's something I'd like you to see about this truss. You see we have 20, 20, 20 kilonewtons. We have 4 meters, 4 meters, 4 meters, 4 meters, and 3 meters. There's an awful lot of symmetry. So basically what's going on one side of the truss is going to be going on the other side of the truss. So if you solve half of this truss, you can solve the other half just by writing it down. The other thing is A is a fixed support. Oops, you can't even see this. Dang it. All right, here we go. Let's try again. Lots of symmetry. 4 meter, 4 meter, 4 meter, 4 meter, 3 meter tall, 20 kilonewton loads at each of these joints. Even though A is a fixed support and E is a rolling support, there are no horizontal forces on this truss. That means that there will only be a reaction at A in the y direction, and there will be a reaction at E in the y direction. There's no x-directional forces externally on this truss whatsoever. That's right, there's nothing counteracted, so it would start moving if we did. Right. And bridges actually act like this quite a lot. If you have a bridge truss, most of the loading is y-directional because you have cars and stuff going across it. So there's really not a lot of x-directional forces. Okay. All right. Any questions so far? Well, let's look at the method of sections. This is also, and I will, by the way, with this homework assignment, this will be posted. It will say homework number 1, do problems 614, 621 using the method of joints, and then it will say do 2 more problems using the method of sections, which we're going to start talking about today. So you'll have a total of 4 homework problems, but if you write this down, it will give you a head start, but it will be in an explicit place on the Moodle page as well. So it's not like you have to pick through everything to find out what your homework is. I'll make it very, very clear so that you'll be able to stay organized with that. All right, so the next thing that we're talking about today is the method of sections, and this is the handout that I have given you today, and it's also posted to your Moodle page. But I just want to show. I just wanted to orient you, but I will. I'll work on the document cam in just a moment. Okay. Now, the reason that we would use the method of sections, you can almost always use the method of joints for any truss. But sometimes the trusses become very complicated. This truss, for example, you'll see we do have a horizontal force applied to it. So A will have a y-directional force and an x-directional force. And also, if you look at the forces, the vertical forces that are applied, 10 kips, which is 10,000 pounds, 20,000 pounds, and 30,000 pounds, this is not symmetrical. So even though the geometric truss, the physical truss has symmetry, the force truss will not have symmetry. So you're going to have to solve everything. So if they ask you, what is the force here at in GC or GH, you would have to chase this a long way. You would have to say, okay, here's at A, get my reactions, here's this force and this force, chase it over here. You're going to find out that you have too many forces and you can't actually solve this, because remember, we only have 2 equations and 2 unknowns per joint. So you might come up here and do this one, and then you'll come up here and you'll say, well, there's 3 forces, 3 unknowns, 2 forces, can't do it. You may start here and trace it back. You may be able to solve it explicitly using the method of joints from both sides, but it's quite complicated. So the method of sections is a way to get into the internal pieces of this truss without having to chase for 1,000 years, without having to do every single thing. So in other words, if you would like to just know G sub H, what we do is we look at a section of the truss. And in the same way that we can look at a joint and we can say all forces into a joint have to vectorially sum to 0. We can also say if we just look at a piece of the truss, a piece or a section, otherwise known as a section of the truss, the summation of forces vectorially into that, about that section, also have to be 0. But because a section is not a point, we have a third equation. The summation of moments on any point on that section also has to be equal to 0. So when you do the method of sections, you don't just have the summation of forces x, summation forces y. You also have summation of moments about any point on the section. So what we're getting at here is on this example, you can go ahead and redraw the truss a little bit, and then I'll do the section that they talk about. There's 1, 2, 3, 4, 5, 6. That's kind of 1, 2, 3, 4, 1, 2, 3, 4. Okay, so I've abbreviated this one. I apologize. This actually has more symmetry than I've drawn. That's just my drawing skills. That's why I like Ernie and the state of Wyoming, because this is what the state of Wyoming looks like. It's easy for me to draw. Montana, Idaho, other things, not so much. But Wyoming looks like this. Truss looks kind of like this, but my drawing prowess has failed me at this end. Okay, so If we do an analysis, we know that we're going to have a reaction at A in the y direction, a reaction at A in the x direction. We're going to have this applied load of 15 kips, which is a positive x directional force. We see that E is a rolling support, so we can just have a reaction at E in the y direction. There is no possibility that we could have a reaction at E in the x direction because it's a rolling support. We then have a 10 kilopound force here at B and a 20 kilopound force here at C and a 30 kilopound force here at D. Okay, if we wish to know the reaction here, this is GH, or the reaction here in GC, we can also look at a section of the truss. And when I say that, what I mean is, after I find these reactions at A and at A, using the entire truss, I can just cut a section, and then I can either look at this side of my cut or this side of my cut. So if I'm interested, if I see this, I see that I have three sections here, or excuse me, three cut structural members is what I attempted to say. I can view all of these that are cut as forces and everything else as just this section of truss. So I can look at it as just having RAX, RAY, and this 10 kilopound force acting on it, as well as AG, GC, and whatever this one is, BC. Okay? So what I guess I'm saying explicitly is that I just look at this chunk of it as being a piece, and then I have 1, 2, 3, 4, 5, 6 forces acting on the piece. So I can do my free body diagram with the entire truss, just like I did with the method of joints, but now I can also look at the method of sections, just looking at this section that I've drawn in blue and looking at these forces acting upon it. And on this section, I can say the summation of forces in the x direction on the section have to equal 0, summation of forces in the y direction on the section have to equal 0, and the summation of moments on any point of this section also have to equal 0. So anything that I've cut, I have to use as a force, but I don't have to deal with the internal forces in anything that is uncut. It's just part of the section. So that eliminates a whole lot of work. Okay? Now we're out of time for today, but I'm going to save my work. I will not erase it. And when we come back on Friday, I will flop this right back up, and we will get started from that point. All right? All right, that's it for today, ladies and gentlemen. Thank you for your time, and we'll see you Friday for more fun with method of sections.